All right, so we're going to learn about exponential growth and decay. So some of this we've already seen before, and you've probably seen it in other classes as well. So of course, we're going to add the calculus to it this time, but not going to be a big deal. So suppose you have an item currently worth $5,000, or whatever it is worth, and is increasing 8% per year. So what does that look like over time? So after year one, that item would be worth 5,000 plus 5,000 times the interest rate. And if we could factor out a 5,000 in this, so we have 5,000 times 1.08, or 1 plus 0.08, which is 1.08. And then whatever that is, not worried about what that is. But then after the second year, after year two, it would be the 5,000 times the 1.08 that it is after the first year. And then we're going to add another 8% to that. So we're going to multiply again by 1.08. And then simplifying that, we get 5,000 times 1.08 squared. And if we did it again, we can see after year three, it would be 5,000 times 1.8 to the third. And so whatever year we're in, we just continue the process after year t. Then the item is worth 5,000 times 1.08 to the t. And so that's the formula for if something is increasing at a particular rate per year. So this is exponential growth. And then we could also do the same thing with decreasing. If we are decreasing, we have a decreasing rate, all we're going to do is do the subtraction. So if we were decreasing at 8% per year, then it would be 5,000, and instead of 1 plus 0.08, it'd be 1 minus 0.08 to the t, or 5,000 times 0.92 to the t. All right, so it just depends if it's increasing or decreasing, and we get an exponential equation. So for the first example, we have a used Cessna 172 Skyhawk. It is purchased for $56,000. Buyer predicts it will decline in value 3.8% each year. So this is a decline. So we're going to use the decreasing rate. So our decreasing rate would be 1 minus 0.038, which is 0.962. And so now we'll probably usually use A of t. Actually, we're using V of t, since it tells us that. So V of t will be the initial amount, 56,000, times 0.962 to the t. And so that's going to tell us the value after t years, whatever t is. And so then B says, what is the predicted value of the plane 4.5 years from now? So we're just going to get B of 4.5. So 56,000 times 0.962 to 4.5. Just put that in the calculator, and we should get 47,041. Like so. All right. Then C is a little bit more algebra. C is a little bit more algebra. So how long will it take for the value of the plane to decline to $20,000? So we're starting at 56,000, decreasing over the years. So how long will it take to get down to 20,000? So we're going to set this equation equal to 20,000 and solve for t. So 20,000 equals 56,000 times 0.962 to the t. And so you need to get pretty comfortable with solving these if you're not already. So the first thing we do is we want to get the exponential expression by itself. So we want to get 0.962 to the t by itself, and then we can work on getting the t by itself. So we're going to divide by, I need to get my calculator. We divide 20,000 by 56,000. And we get 0.357143 equals 0.962 to the t. Usually, so whenever you're doing these calculations, especially these, because you're going to get decimal answers, and you don't want to have rounding errors. So normally, whenever I do any calculation, while we're in the middle, leave at least 6 digits in your process so that you don't have a rounding error at the end. Because normally you're going to round it 2 digits or 3 digits. So if you round off at 6, then you're not going to have the rounding error. All right, so now we need to convert this, or take the ln of both sides, or convert it to a logarithm equation. So take the ln of both sides, ln of 0.962 to the t. We'll go ahead and bring the t down in front of that. So we have t ln of 0.962, and then we're just going to divide both sides by that. And we get t. And so the t should come out to 26.5. Okay, so far nothing really that you wouldn't have seen in an algebra class. I'm just kind of setting these up and solving for t or solving for b or whatever it is. All right, so next topic, now we have compound interest, which probably also have seen in algebra classes. So in compound interest, investing money, and we're just going to give you the formulas. So if we have money that is compounding annually, and this will work the same way as the last example. So A of t, A for accumulated amount, equals P times 1 plus R to the T. So that's just every January 1st or whatever date of the year, we're accumulating interest on that date, and then that's how much we get in the year, and then we can figure out over a certain time period. Now, if we want to do more frequently, like quarterly, monthly, or semi-annually, or whatever else, now it's just slightly more complicated. And we won't go through how to derive this right now, but we have P times 1 plus R over N to the NT. Now, what is N? N is the compounding periods. So if we're quarterly, there would be 4 compounding periods. I guess we add per year, compounding periods per year. So quarterly would be 4 compounding periods per year, monthly 12, semi-annually 2, that kind of thing, daily 365. And then we have compounding continuously. So then we have A of t is P e to the RT. So whenever we have continuously anything, continuous decay, continuous growth, compounding continuously, we're going to use the e function to find that, which essentially is what we get if you take n to infinity. So continuous compounding, we're have n compounding or infinite compounding periods per year. And if you take the limit of that as n goes to infinity, this is what you get. All right, so example 2, we have 25,000 invested at 3.2% interest. Find the value of the account after 5 years if it's compounded quarterly. So just very straightforward plugging this in. So we're going to use the second formula up there. So 25,000 times 1 plus 0.032 is compounded quarterly. So our n is going to be 4. And then 4 for n, and then we're compounding for 5 years. And we can just plug that straight into the calculator, and we get $29,319.10. Right. So easy enough. Then compute the account value after 5 years if the interest is compounded continuously. So now we're going to use the E function. So P e to the RT. P is still 25,000. E and then 0.032 times 5. And we should get 29,337.77. And this brings up a little point. As long as everything else is equal, the more compounding periods you have, the higher the money will be after the same period of time. So we have 5 years, same interest rate, same beginning amount, same principal. The only thing that changes here is here we had 4 compounding periods per year. Here we had infinite compounding periods per year. So the higher the number of compounding periods in a year, the higher the ending amount will be. All right. So then moving on. So now we have exponential growth, which is essentially the same as the compounding continuously with the money. So formula is A of t, and we just use different letters, but they're representing the same thing. So we're going to use a K. K to KT, E to the KT. And here at K is going to be greater than 0. And K, so a lot of times you'll see the word continuous, but not always. And sometimes it's, I guess you can figure out from the context if it's going to be a continuous or it's going to be a periodic growth, like annual. But other times you'll see what's called the relative growth rate. And so that relative growth rate indicates it's a continuous growth or decay. So K is called the relative growth rate. So you may see that sometimes, and like in this problem. So a lab experiment starts with a population of 4,000 bacteria growing at a relative growth rate of 7.2% per hour. So find the population and its rate of change after 3 hours. So of course, rate of change is going to tell us that we need to find the derivative. So let's write our formula. So A of t is 4,000 e to the 0.072 t. And we're going to find A of 3. So 4,000 e to the 0.072 times 3. And that is 4964. We're going to cut off all the decimal, round to the nearest integer because we're talking about bacteria. So we're not going to worry about a fifth of bacteria or whatever. And then find the rate of change. So rate of change indicates we need to find the derivative. So A prime of t. And so we're going to just write the exponential function and then take the derivative of the exponent, which of course is 0.072. And so 4,000 times 0.072 is 288. So we just have 288 e to the 0.072 t. And then find A prime 3. So 288 times e to the 0.072 times 3, and I'll convert t again instead of 3. And we get 357.437. Right. And then how long will it be until the population reaches 18,000? So this one is going to solve the equation for t. So how long indicates we're looking for t. So 4,000 e to the 0.072 t. And so just like on the earlier one we saw, we're going to get this exponential expression by itself. So we're going to divide both sides by 4,000. So we get 4.4 equals e to the 0.072 t. Now ln both sides. And divide by 0.072, and we get that t is 20.89. And does ask, probably on website it will not ask for this, but it is hours, not years or days. All right. Now radioactive decay. And so here we're going to talk about a term that I'm sure you've seen before, and that's the half-life. So half-life is the time required for half of a given quantity to decay. We have the same formula. A of t equals c e to the k t, but here k is going to be less than 0. So that's the only difference. All right, so next we have number 4. So the half-life of a radioactive material, radium-226, is 1,590 years. Start with 100 grams, milligrams, 100 milligrams, and find the formula for the mass after t years. So we kind of shortcut this with without using the e. And so when we're talking about half-life, we can just make the base be a half and then divide by whatever that half-life is. So there's our formula, and that's still we could convert that to an e expression, but we don't need to. You can just leave it like that. And so then let's find a of 1,000, the nearest milligram. Oops, 100. And we should get 2762 for that. And then how long will it take to be reduced to 30 milligrams? So 30 is 100 times 1/2 to the t over 1590. Divide by 100 again. So get the exponential expression by itself. So get the 1/2 t over 1590 by itself. Divide by 100, and we get 0.3 is 1/2 to the t over 1590. Log both sides, ln both sides, whatever you like. Ln of 0.30 equals, then we're bringing the exponent down as we do the logarithm. And then we can, essentially we're going to multiply by the 1590, divide by the ln of 1/2. So we end up with, and we'll put this in the calculator, but 1590 times ln of 0.3 all over ln of 1/2, or ln of 0.5. And we should get 2762, which is t. All right, so far we kind of been doing similar things over and over again. All right, at what rate is the mass decreasing when 30 milligrams remain? So we need to take the derivative So, whoops, A. So our function is A of t is 100 times 1/2 t over 1590. So we're talking about the rate, so we need to take the derivative. And so anytime you do an exponential, you just write the exponential and then work with what you need to work with. And so whenever, if the base is not e, we always take the logarithm, or the ln, sorry, of that base, which you do anyway when it's e. It's just ln of e is 1, so you don't have to worry about it. And then times the derivative of the exponent. Okay, I just noticed this up here is not that. I looked at the wrong spot. That is 64.7. Now, at what rate is the mass decreasing when 30 milligrams remains? So we found up here that that is at t equals 2762. So we just need to find a prime of 2762. And plug that in the calculator, and we get 0.01308. Okay. All right, so the last thing is another financial problem. $16,000 is invested in an account, earns 4.3% interest. Write an equation for the function b that gives the value of the account after t years compounded monthly. So we have v of t is started with 16,000 times 1 plus 0.043. N is going to be 12, and then to the 12t. And then find v prime of 3.5. So we got to take the derivative. And so I would recommend just leaving, obviously you can put that in the calculator, but again, you end up with rounding issues. And a lot of times WebAssign, if it doesn't tell you to round, then you should not round. And when you put in, let me see what we get, 0.043 divided by 12, you get a continuous decimal. So it's 1.0035833 repeating. So if it doesn't tell you where to cut that off, I would just leave that in there like that and not get the decimal, because wherever you cut it off is wrong. So we're going to do the same thing with the derivative. So we're just going to leave it like that. And then we have to multiply by the ln of the base. And then times the derivative of the exponent. So anytime you do any exponential derivative like this, you always just write the exponential part. That's, of course, a constant, so it's not changing anything. Write the exponential part like that. Do the ln of the base, which if it's e to the 12t, it'd be e to the 12t times ln of e, which is just 1, so that goes away. And then times the derivative of the exponent, which is 12 in this case. And then we're going to find v prime of 3.5, and we should get, plug all it in, 798.10. Okay, so not too much to this section. There's just a few basic formulas, and other than maybe this one, they're pretty easy. Like this one is a little bit more complicated as far as what you need, as far as remembering it, I guess. But nothing's too tricky. You want to make sure you get good at taking these derivatives of the exponentials, and other than that, probably just get familiar with the vocabulary like relative growth rate and what formula goes with what, that kind of thing. All right, so email me if you have any questions.